Welcome to STEM Research website. This is a website which contains several applications that you can use in your mathematical analysis or to do computations online. The applications are available here. Just access them by clicking the menu, this top icon here, button up here, then select apps, STEM apps. It will take you to the applications page. Alternatively, you can just search for any application from this drop-down menu you can see here. For example, if I wanted any application, the differentiation application, if I just type differentiation, then I can find the application here. I click on it. It should open the differentiation page. But I can access the page with all the applications by clicking STEM apps like that. So these are the applications that we currently have uploaded to the website. There are more applications only that we are uploading them little by little. So you can look at them. Now I want us to demonstrate just two such applications. One of it would be, for example, want to do implicit differentiation in using Python. So this link will take me to that. So I simply click on it. And then it opens this implicit differentiation page where I insert the value. So in this case, we want to find the implicit derivative, the third order implicit derivative of this expression here with respect to x and y being the dependent variable. And then we want to factorize the results. So with assuming that we're going with these values here, you simply click the integrate button and it will give you that derivative, the implicit derivative. So this is the result, but before we come to the result, I would like us to look at the main page, the main tab. The main tab gives you information about all these input fields and what each one of them represents. You can see these are the input fields as you see them here. And then this is a description of each of the input fields. The one that you cannot see here is import libraries. It's not shown. And then this shows you the inputs that you have entered. So each of the inputs you have entered here in this section here will be displayed under this column, the last column. So our results, to see the results, you go to the results tab. Of course, that will always be the default tab. Anytime I click, this one will always be activated by default. So now we are saying that what we wanted was the third order derivative of this multivariate function. It's a function of two variables, x and y, as given here. So if we did that, then we find the third order derivative with respect to the variable x. And as we said, y is the dependent variable in this expression here. We consider y as the dependent variable. So this is the answer that we are finding. Of course, you can write this answer, rewrite it in different ways by changing the method here. For example, if I choose on simplify, you get the same expression, only that it's written in a different way. If I say none, there's no simplification being done. You get some different result. If I say group together, I forgot to click differentiate. So you get that and so on. So you can always change this to get an expression that you feel looks close to what you like, or in its most simplest and readable format. Then of course you can always change the order of the derivative by changing it here. So this is the first derivative. This is the second derivative, the third derivative you have seen. The fourth derivative will be given by that expression, and finally we only have up to order 5. Will be given by that expression. Now, so the next tab is the Python syntax tab. So this gives you the syntax, Python syntax for doing what? For getting these results, we have here. So let me go back to the third order where we were. So this we want to see how do we differentiate this expression here implicitly with respect to x given y as the dependent variable to order 3 using the Python software. Of course, in this case, we will be using the SymPy package. So by default, well, not by default, this application here is designed to generate syntax for every procedure that you are going to run. So just click here. Then this is the syntax. So the first thing is that you must start by importing these first two lines. These first two lines are the importation statements. So we have said that we're using the SymPy package to do the derivative. So we first import it. Then this one here is just a function to ensure that we get the printing of the expressions clearly. So for example, I just let me copy this, just copy that, go to Python, open a new notebook. So click Python 3. It opens a new Jupyter notebook. Paste those importation statements there, then press the enter key. So they have loaded successfully. Now I go to the syntax. So this is the syntax. I just copy now from here up to there. Copy, paste it in any cell. I can just take some short time to explain what this is. For this first step, I'll say that this is mandatory. I must first begin by importing the SymPy package, assuming that it had not been imported earlier. Then the first statement is I need to declare the functions of that given expression as symbolic variables. So I'm telling SymPy that x and y in this expression that I want to enter are symbolic variables. Then next I define the expression itself, and I must define it using the SymPy namespaces. So because I've imported SymPy as sim, then I have to say, for me to get a function, for example, the square root, I must prefix it with sim dot. Then again, the arcsign function, I do the same. So this just defines that equation we had, this equation here in SymPy. So like that. Then now here's where we get the derivative. We are telling SymPy to differentiate this expression here implicitly. So it is I must start by I. I is the implicit derivative in SymPy. Then I specify that expression. So I'm telling it's this expression that I'm referring to. Then I define the dependent variable, which we said is y. Then I define the independent variable, which is x. This is now the variable we are differentiating with respect to. Then I also specify the order of differentiation, which is order 3. That's all I need to carry out implicit differentiation in SymPy. Of course, the next last line here is simply to display the results, both the function that we entered, function that we entered, which is this expression here, and the result. The result we said we defined it as derivative. So I'm just displaying it and using together to simplify it, right? Or rather to rewrite it in a simplified way. So with that, I'd simply press the enter key. So it's processing. So that's the equation we entered. Then this is the third order derivative, implicit derivative of the function that we entered. So that is it for the implicit differentiation application. The next application I would like us to look at is to find the Jacobian of a matrix. So to do that, just come to this menu and then click, type Jacobian. It will search for Jacobian. then click on it. So this is what it opens up in this page where you specify the systems of equations here. Then you specify the dependent variables in this text box here. Then you specify whether to find the solution at equilibrium points or not. By default, it's true, but someone can choose not to find those solutions and so on. So for us, we are choosing to find the equilibrium points of the Jacobian matrix that comes from these equations here. There are 3 equations, and 2, you find the solution at each of the calculated equilibrium points. So with that information, you simply click linearize, and you get the results as follows. So again, the main tab gives you the information, what you have entered here, the user inputs and what you have entered. For example, these are the matrices, the system of equations that has been entered. These are the dependent variables, and then we are choosing to show to find the solution of the Jacobian matrix at the calculated equilibrium points. So with that, we go to the results tab. So again, we see that this is our equations. These are our system of equations, the first one, the second one, and the third one. All of them are in symbolic format. And here now we get the result that this is the Jacobian matrix of this system of equations that we entered. Then the calculated equilibrium points are as follows. We have X. These are the solutions of this Jacobian matrix. There are quite a number of them. You can scroll to see them. Then now this is the value of the Jacobian matrix at the given equilibrium points. For example, for this first equilibrium points, the value of Jacobian matrix is given as that. In short, we are saying you substitute for X is equals to 0, Y is equals to 0, and Z is equals to 0. In this matrix, you are going to get this new matrix here. The same applies to all these other equilibrium points. So now we go to the Python syntax and just click that. And then we start by the importation statements. But because we know that we already have imported this, we just can skip this line, these 2 lines, and go to the syntax straight away. So I just copy the whole of that syntax, then paste it here, then press the enter key to get the result. So we get the results. First, it's printing the system of equations that you have entered. Then the next, it will print the matrix form. Okay, the system now you entered in matrix form. It will print the Jacobian, as you can see. Then it will print the equilibrium points, as you can see here. Then next, you now begin to print the solutions, rather the value of the Jacobian matrix at these equilibrium points. So it has printed the 3 values. It's actually similar to the results that we found, only that this time we are not printing them horizontally, but we are printing them vertically, like that. So that is all to do with this Jacobian application. And then the last application I can demonstrate is plotting functions using this application. So just scroll to the bottom last value, or it's easier to search here. I just type plot. Plot will filter out all the rest, give me that. So just click on it. So you enter quite a number of inputs. The most important is that you need to enter the expression for which you want to plot. You need to enter the upper and lower and upper bounds, or rather limits. Then you need to specify either the step size and specify it here, or you can specify the number of steps and then you specify an integer here. Then you can specify the X and Y limits. By default, none is specified, but you can specify your own here. Other additional options are given here. You can specify the line properties, marker properties, and many other options. Maybe I shall not go into the details of this. I just demonstrate how to do to create the graph direct. So to do that, if you are fine with these inputs here, to get the graph, I simply click plot function. And the graph will be generated as follows. So this is the graph of this function between the points -4 to +4 with a step size of pi/8. So I can see it's -4 to +4, and the step size is pi/8 from here. This is a step size between this, the interval between any two adjacent x values. So that is it. If I wanted to change, for example, to plot a different, for example, if I wanted to plot the graph of x squared, you just change the function like that, then you plot. You can see that that changes that graph. I can choose to, for example, as you said, I use the option of either specifying the step size or the number of steps. So I just specify a number of steps there. Then here I can say maybe 25. Then I press the enter key. I press the plot function. So you can see that the graph has been generated. I can choose to change these limits here. For example, I'm going from -2 to +4. So I'll expect the graph starts at this point. So with that, I can click plot function, and it gives me, it's from -2 to +4 as I've defined it here. Then here, as you say, there are more graph options. As I said, I'll not mention more about this, but I can just change, for example, this one here, I can change the color, the plotting scheme. To remove this background here, I can choose to use a different scheme. I know there is one known as fast to remove that background. Then click. So this is the new graph that I find. So thank you for watching this video. We welcome you to our website to use the application to do your mathematical computations online. Thank you once again.